First stage, main engine ignition. Lift.
Okay, this is a video looking at an introduction to orbits. It's given and developed primarily as part of the undergraduate option in remote sensing of global change at the University of Edinburgh. Now you might all have some kind of idea of what we mean by an orbit. Of course, this is a description of the satellites rotating around the Earth. In this course we're almost exclusively considering satellite measurements of the Earth. So understanding orbits and the influence that they have on the measurements that we make is quite a vital part of understanding the data, what we can measure, how fast we can measure it, the coverage of the planet. This video comes from NASA. It's a video showing a collection of NASA environmental satellites, obviously not to scale. Those little yellow blobs there are just representative. Real satellites are in the scale of a few meters to tens of meters. So roughly about the size of a car to a large double-decker bus is about as big as Earth observation satellites get. Now you'll notice that they seem to be orbiting the Earth in slightly different ways. All these satellites seem to be roughly the same altitude above the Earth's surface, but they seem to be going in different directions. They seem to be going, some of them seem to get nearer to the poles than others. So there's clearly a variety of different ways in which we can have a satellite orbiting the Earth. The other thing that this diagram, this animation doesn't show is the area of coverage, the area of measurements on the Earth's surface or in the atmosphere. So here's a video actually showing you the coverage of the measurements of this satellite. This just happens to be the Aqua satellite. It's another short video here from NASA, and it's showing you the that sort of purpley blue band beneath the satellite is the width of the measurements that the satellite is taking. So you can see the little green lines are the scan lines of the measurements that it's taking. It doesn't matter if it's taking measurements of the atmosphere or the Earth's surface here. It just gives you an idea of the coverage of the measurements. This is quite a wide swath of measurements. So the width of this path, this swath, is actually so wide that when the satellite comes around for a second time, it actually overlaps with the first pass. Now if it takes about 90 minutes for a satellite to orbit the Earth, then you can see that maybe a dozen times, so about a day or not much more than a day, you can have full coverage of the Earth in this particular orbit. The orbit goes up and over the poles, and it comes down around the equator, and so it covers all parts of the Earth because of the overlapping swath. Now not all satellites are like that. And clearly the width of the measurement swath, so the range of the geometry of the measurements has an impact on how much area is covered. But also the satellite flying altitude has an influence on how much that apparent coverage is on the Earth's surface. Here's another satellite with a slightly narrower swath. It's actually the same satellite, still Aqua, but it's a different instrument, and it's now scanning over a smaller area on the Earth's surface. So you'll notice that when it comes around for the second orbit, at the poles it actually crosses over, but as you reach the equator, there's actually a gap in the coverage there. And clearly if you went to a satellite with an even narrower swath, the gap in the coverage would get larger, and it would therefore take many more orbits to get around the planet in order to get full coverage. Some satellites in fact have such narrow swaths that it can take a whole month before the entire surface of the Earth is covered using this kind of polar orbit. You'll also notice that because the Earth is rotating underneath the orbit, so the satellite is going around in its orbital plane, and the Earth is turning underneath it, that it means that the polar regions actually get covered very well. There's lots of measurements at the poles, and the equatorial regions are the ones most likely to have the gaps. So getting full coverage at equatorial regions from this kind of orbit is harder to do than in the polar regions. So why do we need to think about the types of orbit? Well, the key thing that I've mentioned already is that the choice of orbit actually determines the frequency of the measurements. So am I going to get measurements of the, say, the atmospheric temperature every 24 hours, or is it going to take a week before I get the measurements? These kind of questions are very important. Some measurements, like global biomass, it may be sufficient to measure on a seasonal basis, so maybe averages of or measurements every 2 weeks or every month. Measurements of sea surface temperature or dynamic weather events, you might want to measure very much more frequently than that, down to a few hours. Or in some measurements, we'll see in a minute, where instruments appear to actually be above the same part of the Earth all the time, you can actually make measurements every 15 minutes. The flying altitude clearly has a choice here because it has an influence on the level of measurement detail. The closer you are to the Earth's surface in general for most kinds of instruments, the more detail you can see, but the harder it is to get global coverage. Not all instruments, by the way, are like that. Some instruments, like radar instruments, actually the level of detail is not governed in the same way by the flying altitude. And these are both really the flying altitude, so the size of the swath and the level of detail and the frequency of measurements, they're both related to the data coverage, whether that's on the surface or in the atmosphere. The choice of orbit also influences the lifetime of the instrument, simply because if you're in the lower the orbit, the lower altitude, the more likely there is to be a little bit of the upper atmosphere still present that will induce drag and friction and ultimately mean that the satellite will have a shorter lifetime. If you actually take on fuel, you can potentially keep yourself in a stable orbit even at quite low altitudes of a few hundred kilometers. Or if you're only up for like the space shuttle for short periods of time, then that's feasible. But ultimately it's potential constraint on the lifetime of the instrument. And there's also the question of data download capabilities, because depending on how much data you're trying to download, at any one point you might be trying to measure a part of the surface of the Earth, but you also have to be able to effectively, the satellite has to see the downstation on the Earth's surface to actually transmit the information that it's collecting into a ground station that can then be collected and used. Of course, there's not sufficient coverage of ground stations to do that all the time, so what satellites tend to do is store the data on board. But then you have a capacity problem in terms of how much storage can you have on board before you actually can download it to the next downstation. So all of these parameters are related to the orbit. And the final thing is the cost of launch. That tends to be more an issue of practicality rather than from the science perspective, because to get it into higher or more complicated orbits ultimately costs more money. Okay, let's consider some of the physics of orbits. How do you actually get a projectile into orbit? Now, the best way to think about this is, let's take a rifle. So this is us standing on the ground holding a rifle. What we're going to do is fire a projectile, a bullet, out of that rifle. So we fire that projectile horizontally and we look to see where the bullet's going to go. The temptation to think, of course, is that the bullet would just keep travelling in a horizontal line, and that it's actually air resistance that slows the bullet down and makes it fall to the ground. But that's not strictly true, because as the bullet travels along, it's subject to a very important force, which is gravity. And gravity pulls the bullet down towards the ground. Now, of course, it's not towards the ground so much as towards the centre of the Earth. So the actual trajectory of the bullet is such that it falls in a parabola until it hits the ground. And that's simply because gravity is pulling it down towards the centre of the Earth. Now, of course, the Earth is not perfectly flat, but the Earth is curved. So what happens if we actually fire our projectile fast enough that even though gravity is pulling on it, so we have this curvature of the motion of the bullet is actually bending towards the center of the Earth, that the Earth underneath is actually also curving away. So what happens in that condition? Well, of course, what happens is that the Earth curves away underneath, and the trajectory of the bullet is such that although it's bending round and going towards is being pulled by Earth's gravity towards the center, the curvature of the Earth is actually falling away underneath it. So the bullet's trajectory is a curve bending towards the center of the Earth, but the Earth's surface itself is also bending round. So let's take a step back and look at this at a bit larger scale. So here's our Earth, and here's us firing our projectile. So again, we fire the projectile, our bullet, horizontally. Now we could imagine that if we fire this bullet with enough energy, its trajectory would actually be completely off the planet and very, very far away. And in fact, that's where, if you're sending interplanetary probes like Voyager, or the various other missions, more recent missions like Galileo, that's what you do. You fire your projectile, your planetary probe, with such a force of energy that the gravitational pull actually doesn't have very much influence on it. It has some influence on it, but not sufficient to actually bend it round into orbit. If we don't fire it with enough energy, if we don't give enough energy into this projectile, then the path of the projectile simply, as before, just goes straight into the surface of the Earth in a nice straightforward parabola. The trick is to fire our projectile in such a way that it has just enough energy that it doesn't leave the planet's gravitational influence altogether, but it's got enough energy to not crash into the surface of the Earth. So we're effectively firing our projectile over the horizon. And of course, at any particular point that you want to consider it in this orbit, this projectile is travelling at a particular velocity parallel to the surface of the Earth. It's under the influence of gravity, so that gravity is still pulling at all times. Gravity is still pulling this projectile towards the surface, towards the center of the Earth. But it has enough horizontal momentum to actually keep going all the way around. Ultimately, as a projectile, you don't want to be at the receiving end of that, because the projectile has travelled all the way around the world now, always under the influence of gravity pulling it towards the center, but its horizontal momentum means that it always goes over the horizon and never actually is pulled down to the Earth's surface. Of course, it arrives back to where it started from, and as the person who shot the gun, it would arrive back and hit you in the back of the head. But of course, we're not looking at projectiles of bullets, we're looking at individual satellites. So satellites about the size of a car or a large bus, quite a few meters. We're going to send it with such sufficient horizontal momentum that it's going to get above the atmosphere, so there's no more atmospheric resistance, and it's going to keep moving because there's no reason for it to slow down. It's going to keep moving at that horizontal velocity, and although gravity keeps pulling to the center, it comes all the way back again. It curves round over the horizon, and effectively will keep going round and round until at such point perhaps the influence of some of the upper atmosphere slows it down, that it might eventually crash down to the surface. But in principle, if we ignore the atmospheric resistance, is that this projectile can simply go round and round. That's what we mean by putting something into orbit. Okay, so we've seen how the physical dynamics of an orbit is such that we have an object, which is our satellite, that's rotating in a plane around the Earth, and the Earth is rotating underneath it. Because it's gravity that effectively drives the dynamics of the orbit and is always pulling the satellite towards the center of the Earth, it means that there are orbits which are not possible. So if the orbital plane does not cross through the centre of the Earth, then that orbit is not physically realizable. There are, of course, a number of different ways that you can have orbits. So these three examples here. The red one is an equatorial orbit, so it's rotating around the equator. The blue one is a polar orbit because the orbital plane is over the poles. You can also have a near polar orbit where it's not quite going exactly over the poles but is very nearly to the poles. And then the green orbit is inclined at about 45 degrees. The blue orbit and the polar or near polar orbits are very common for many of the high resolution imaging systems used in Earth observation. And the red equatorial orbit, we'll see shortly, is very important in the context of what are called geostationary orbits, which are equatorial. Perhaps the most complicated notion to get to grips with in looking at orbits is this issue to do with orbital precession, which we're going to take advantage of because what we see is that the orbit, as the orbital plane, as the satellite orbits around the Earth in this orbital plane, because of the shape of the Earth, the orbital plane actually precesses round, so it rotates round over time. Now, the exact time it takes to precess all the way around is dependent on the characteristics of the orbit, the inclination angle, the altitude. But one very clever thing you can do with this precession of the orbit, if we look at the solar system scale now, so this big yellow ball in the middle is the sun, and the sort of bluey greeny ball with a white tip on it is the Earth going around the sun. So that takes 365 days. It's a 1 year to get all the way around the sun. But you'll notice this red plane now of showing the precession of the orbit of the satellite around the Earth is precessing in such a way is that it's always pointing to the sun. So in fact we can use this in a very clever way so that the satellite is always passing the sunlit side of the Earth at the same solar time of day. So the way this particular animation is done is that it's effectively noon. So the satellite is always passing overhead at noon in this satellite situation. Because it always passes relative to the solar time, this is what we call a sun-synchronous orbit. There's certain advantages, especially for optical sensors, to measure at the same time of day. The solar illumination is the same. If we measure, many of them will measure around about 9 or 10 o'clock in the morning when the cloud cover is at its lowest. And of course it has a nighttime pass as well, but the optical sensors that are using solar illumination can't actually make any measurements. But that's not a problem. But sun-synchronous orbits can actually also be tilted in different ways, so you can pass at certain times of the day, depending on whether or not you're wanting to measure at a fixed time of day every day. And of course when I say time of day, that's relative to the sun. It's a solar clock here. So that's a sun-synchronous orbit, which is perhaps the most difficult one to get your head around. One of the key things about an orbit is that the higher altitude you go to with your orbit, the longer it takes for the satellite to get all the way around. So the orbital period increases as you get to higher and higher altitude. In this plan view here, so we're looking down on the North Pole of the Earth, we'll see that if we actually choose a satellite that has an orbital period of 24 hours, then the satellite is actually rotating all the way around the Earth in the same time as it takes the Earth to rotate once. So 1 day. And what you can see from these animations, so there's the one that's the plan view, and then the one in the bottom right here is actually showing sort of a perspective view, is that the satellite goes round, but the Earth is also rotating underneath it at the same rate. And if you put that satellite into an equatorial orbit, what this means is that it's actually looking at the same, or it appears to be directly above the same point on the Earth all the time. We call this a geostationary orbit because it appears to be stationary relative to the Earth. So geo meaning Earth and stationary. You can also have geosynchronous orbits which take 24 hours to go around but aren't in an equatorial plane, so they actually move relative to the Earth's surface, but they still take 24 hours to rotate around. But geostationary orbit is the interesting one because it's used as one of the key orbits in Earth observation for looking at meteorological phenomena, so weather satellites. Meteosat is the European one, which is over the Greenwich meridian and equator, so 0 degrees north and 0 degrees east-west. The Americans also run what are called GOES East and GOES West, which are two geostationary satellites over the Americas. Japan runs one and Russia also runs one. So together these 5 satellites cover almost the entire globe, and they make measurements at a rate of about 1 measurement every 15 minutes. Of course, these instruments don't see the poles very well. They only see the equatorial to mid latitudes at very frequent measurements, but they don't measure much of the polar regions because of their viewpoint, their vantage point. Okay, so to summarize and round up here, that this is just a diagram to help you remember that there's 2 main orbit types that we're interested in and will come up frequently when you'll start looking at sensors. The big green one here is the geostationary orbits, which are almost exclusively used for weather satellites, but we also include that measurements of the Earth radiation budget, so how much radiation is arriving and leaving the Earth's surface. And the yellow orbit here is to represent the polar or near polar orbits, which almost exclusively, almost all the satellites that you will look at in this course will be in a near polar orbit, because it provides the best way to get high resolution full coverage of the planet's surface within a relatively short period of time. And relatively short, I mean within a period of about a month. Now, this short video was produced in order to give you a very basic introduction to orbits. And of course, as part of this course, you're also expected to go and look at the online tutorials looking at orbits, which has a number of other little Java applets that you can play about with and get a much more sense of some of the dynamics of orbits. But hopefully this video has given you some basic introduction.